Hi, welcome all to the online classes. I'm Mukesh Bhardwaj. Today I'm going to present a topic, matrices and determinants, which is be taken in elementary maths, BSc Agriculture first semester. So matrices and determinants is an algebra has at least two advantages. Reduce complicated systems of equation to simple expression. Basically, matrices is a mathematical tool which reduce complicated systems of equation to simple expressions, adaptable to systematic method of mathematical treatment and well suited to computers. A definition in matrix is a set of or group of numbers arranged in a square or rectangular array enclosed by two brackets. For example, 1 minus 1 within bracket, O2 minus 3, 0 within bracket, A, B, C, D. These are the pictorial representation or diagrammatically representation of any matrices. Now, properties: a specified number of rows and a specified number of columns. Two numbers, that is row into column, describes the dimension or the size of the matrix. Basically, you may call it the order of the matrix instead of dimension or size of the matrix. For example, 3 by 3 matrix in which three rows and three columns are there, and in each row and in each column, particular in the position, there is one element standouts, and within the bracket it is represented 1 2 4 4 minus 1 5 3 3 3 within the brackets. 2 by 4 matrix, that is two rows three columns, 1 1 3 minus 3 0 0 3 2. 1 by 2 matrix, that is one row and two columns, 1 minus 1. A matrix is denoted by a bold capital letter, and the elements within the matrix are denoted by a lowercase letters. For example, matrix A with elements A, I, J. This is the general representation of any matrix in the form of array, that in the row and columns, where the representation can be, as you see through the diagram, that is A capital bold letter A, M cross N, its size A11, A12, AIJ, AIN, A21, A22, dash dash dash, AIJ, A2N. If I talk about what is the A11, that is any element stands on the position on first row, first column. A12, any element which stands in the position first row, second column. Similarly, A21, the element stands at the second row, first column position. A22, that is on the second row, second column position. So these are the representation of a matrix in a journal. Now, types of matrix. First is column matrix or vector. The number of rows may be an integer, but the number of column is always 1. So, in column matrix, we can say that there must be only one column. Then and then only the set matrix is called column matrix. Rows can be any integer value. For example, 142, that is a column matrix having single column and three rows. 1 minus 3, that is matrix having single column and two rows. Whereas in journal A11, A21, AM1, here am rows are there, but column is only one. Okay, so this is known as the column matrix. Second, row matrix or vector, any number of columns but only one row. That is, column can be as many, but row can be only one. For example, 116, that is one row, three columns. 0352, that is one row, four columns are there. And in general, A11, A12, A13, dash dash dash, A1N. that is n representing the number of columns where the position of all the elements are in the single row. The said matrix is known as row matrix or vector. Rectangular matrix contains more than one element and number of rows is not equal to the number of columns. So any rectangular array or a rectangular matrix, more broadly we can say that a matrix is in the form of a rectangle, that is number of columns and the number of rows are different, or contains more than one element and number of rows is not equal to the number of columns. For example, as you see, the dimension or the size of the first matrix is 4 by 2, that is its rows and columns are not equal. Similarly, for second example, 1 1 1, that is 2 rows and 5 columns are there. So 2 by 5 is the dimension or size or the order of the given matrix. So rectangular matrix is the matrix in which rows and columns are unequal, but the element contains are more than one. Next, square matrix. As the name defines that square is having almost, if I want to define square, square is having all sides are equal. Similarly, in the case of matrix, in we can say that a square matrix is said to be the matrix which is having equal number of rows and equal number of columns. Rows and columns are equal in numbers, then the said matrix is known as square matrix. A square matrix A m by m has an order of m. For example, 1 1 3 0, that is of order 2 by 2, 1 1 1 9 9 0 6 6 1, that is of order 3 by 3. The principal or main diagonal of a square matrix is composed of all elements A I J for which I equals to j. Okay. Diagonal matrix. A square matrix where where all the elements are zero except those on the main diagonal. So a diagonal from top left to right bottom is known as the main diagonal, or opposite diagonal is known as the reverse diagonal. So we can say that a diagonal matrix is a matrix in which the main diagonal elements are non-zero and all the other elements are zero. Then the said matrix is said to be diagonal matrix. For example, as you see, two examples are given of order 3 by 3 or 4 by 4, and the principal diagonal elements are non-zero where all other elements are zero. So we can say this is a diagonal matrix. That is Aij equals to 0 for all I is not equal to j, or Aij equals to not equal to 0 for some or all I equals to j. Unit matrix or identity matrix denoted by capital I, a diagonal matrix with ones on the main diagonal. Specifically, we can say a diagonal matrix in which all the elements of principal diagonal are 1. They are said to be unit or identity matrix. That is Aij equals to 0 for all I not equal to j, and Aij equals 1 for some or all I equals to j. For example, 4 by 4 matrix is shown in which the principal diagonal element contains 1, 2 by 2 matrix in which the principal diagonal contains 1, and again the third example is of 2 by 2 matrix in which the principal diagonal is Aij, that is same. You can, in general, we can say that it is a known as unit matrix or identity matrix. Null matrix or zero matrix. All the elements in the matrix are zero are known as or can be said as null matrix or zero matrix. Uh, Aij equals to 0 for all I and j. In general, we can say that Aij equals to 0 for all I, comma j. So the null matrix or zero matrix is also denoted by 0, or to define, we can say that all the elements in the matrix are 0. Triangular matrix. A square matrix whose elements above or below the main diagonal are all 0. A triangular matrix is said to be a matrix whose elements above or below the main diagonal are all 0. That is, if I'm talking about the principal diagonal, either to the lower below to the principal diagonal or above to the principal diagonal, if the elements are 0, then that is known as the triangular matrix. It is of two kinds: upper triangular matrix and lower triangular matrix. As you in journal see that example 100, that is above to the principal diagonal, all the elements are 0. In the second example, again above to the principal diagonal, all the elements are 0. In the third example, we see that all the elements below to the principal diagonal are 0 and rest of are non-zero. So it is broadly classified into upper triangular and lower triangular. So upper triangular matrix, a square matrix whose all elements below the main diagonal are all 0. It is known as upper triangular matrix. For example, as you see that Aij equals to 0 for all I greater than j. This is the general condition to represent the upper triangular matrix. For example, a matrix of 3 by 3 order. Again, the second example is of 3 by 3 order, and the third example is of 4 by 4 order. So, below to the principal diagonal, all the elements are 0, then we can say this is the upper triangular matrix. Lower triangular matrix, in which all the elements above to the principal diagonals are 0, is known as lower triangular matrix. And in general, Aij equals to 0 for all I less than j. Okay, so this is the triangular matrix and the representation is in front of you. Now the scalar matrix, a diagonal matrix whose main diagonal elements are equal to the same scalar. A scalar is defined as a single number or constant. So we can say that Aij equals to 0 for all I is not equal to j, and Aij equals to A for all I equals to j. So where 1 1 2 2 3 3 stands, that is the principal diagonal elements are there. So the principal diagonal elements are same. So identity matrix can be a scalar matrix. Okay. Uh, Identity matrix is a special kind of a scalar matrix. In Third example, as you see, it is of order 4 by 4, 6000, 0600. So, from principal diagonal contains 6666 and they are non-zeros. So, all the six are all the elements in the principal diagonals are same. So, the elements in the principal diagonals are same, then we can say this is a scalar matrix. Matrix operations. First is equality of matrices. Two matrices are said to be equal only when all corresponding two matrices are said to be equal only when all corresponding elements are equal. Therefore, their size or dimension are equal as well. So, equality of matrix can be defined as, if I want to say that A is equal to B, so A and B can be equal only when A and B are of same order and the elements contained by both the matrices are must be same also. So the A and B matrices are known as equal matrix or equality of matrix. So for example, if I say that A matrix is 100 and second 210 523, whereas B equals to 100 210 523. So we can say that after observing A and B, the orders are same and the corresponding elements standing on the first position, that is first column, first row for A is 1, first row, first column for B is 1, first row, second column 0, first row, second column in B, it is also 0. So each and every element is also 0 and their size is also same. So we can say that A is equals to B. Some properties of equality. If if A equals to B, then B equals to A for all A and B. If A equals to B and B equals to C, then A equals to C for all A, B and C. For example, A equals to this, B equals to this. If A and B, A equals to B, then Aij equals to Bij. So these are the some properties of equality. Now, addition and subtraction of matrices. As a normal algebra for the numbers, we do the addition and subtraction of matrices. Similarly, the addition and subtraction of matrices also be done in a very same way, but here the corresponding element is add or subtracted to the corresponding element of another matrix. The sum or difference of two matrices A and B of the same size yields a matrix C of the same size. So the resultant matrix is of order of the same as A and B, which are added or subtracted. Matrices of different sizes cannot be added or subtracted. So the principal rule for addition and subtraction is that the order of the two matrices must be same. So it's very obvious that different size matrices cannot be added or subtracted. But multiplication can be done for different size of order. But there is some particular rule also. Which type of matrix can we go for multiplication? We will see. Now, The commutative law, A plus B equals to B plus A, very same. Associative law is also holds A plus bracket B plus C equals to bracket A plus B plus C is equals to A plus B plus C. So associative law is also holds good. Now, for example, a matrix of 2 by 3, 7, 3 minus 1, 2 minus 5, 6, and B matrix 1, 5, 6, minus 4, minus 2, 3 are added up. So, as we observe the dimension or the order of these two matrices are same, so they can be go for the addition. 7 plus 1 corresponding elements added up to the corresponding element. 7 plus 1 is equals to 8. 3 plus 5 is equals to 8. Minus 1 plus 6 comes out to be 5. 2 plus 2 minus 4 comes out to be minus 2. Minus 5 minus 2 comes out to be minus 7. 6 plus 3 comes out to be 9. After getting the result, the order is also same for the resultant matrix. Now, A plus 0 is equals to 0 plus A is equals to A, or A plus minus A is equals to 0. One minus A is the matrix composed of minus A, I, J as elements. So, the subtraction for two matrix, for example, 6, 4, 2, 3, 2, 7, subtracted from 1 to 0, 108 is equals to 6 minus 1, 5, 4 minus 2, 2, 2 minus 0, 2, 3 minus 1 is come out to be 2, 2 minus 2 come out to be 0, or 2 minus 0 come out to be 2, and 7 minus 8 come out to be minus 1. So the addition and subtraction of matrix is completed. Now, scalar multiplication of matrices. This is the scalar multiplication, not the multiplication of two matrices. Matrices can be multiplied by a scalar constant or a single element. Let K be a scalar quantity. Then K A is equals to A into K. If K equals to 4, for example, and A is equals to 3 minus 1, 2, 1, 2 minus 3, 4, 1. That is of order 4 by 2, or the size of the matrix given as 4 by 2. 4 columns, or 4 rows, 2 columns. And if K is equals to 4, and if I want to multiply this 4 constant with the A, that is Ka, I want to prove about Ka equals to Ak. So when we just multiply 4 with the matrix, every element is multiplied with 4, and it result into 12, 8, 18, 16, minus 4, 4, minus 12, 4. Similarly, if any matrix A is multiplied to 4, then the same result is come out to be there. And these are the some properties of scalar matrix, a scalar multiplied to the matrix. K A plus B can be written as Ka plus Kb. K plus G, that is again some scalar quantity which is multiplied to A matrix. It can be also written Ka plus Ga. And if a matrix multiplication is there, KAB, ABK, it can be written as KAB, or can be written as AKB. Or the fourth property, KGA, can be written as KGA. Now, very important, multiplication of matrices. The product of two matrices on other matrix. Two matrix A and B must be conformable for multiplication to be possible. That is, number of columns of A must be equal to the number of rows. So we can say that the number of columns of A must be equal to the number of rows of B. Then and then matrix multiplication can be done. Suppose any matrix A is having order 1 by 3. That means its columns are 3 and row is 1. And the second matrix is having order 3 by 1. That is, it's 3 rows and 1 column. So according to the condition for multiplication of two matrices, the number of columns of first must be equal to the number of rows of the second. So they are 3, 3 and they are equal. So the resultant matrix come out to be of 1 by 1 order. So first of all, you need to check out whether the two matrices are multiplied or multiplication can be done by confirming that their first matrix uh, columns are equal to the rows of second matrix. B into A. For example, if we see that a matrix B is of order 2 by 1 and A is of order 4 by 2, so the column of first matrix is not equal to the rows of second matrix. One is not equal to 4. So the matrix multiplication cannot be possible. For example, second, if A matrix is of order 6 by 2, that is having two columns, and the second matrix B is having 6 rows, so we can say that 2 is not equal to 3. So the multiplication of these matrices cannot be possible. And the third example, if A is of size 2 by 3 and B is of size 3 by 2, so A is having 3 columns and B is having 3 rows. So we can say their multiplication can be done and the resultant matrix come out to be of order 2 by 2. In this way, first we need to check whether the multiplication can be possible or not. Now matrix multiplication operation. Matrix multiplication operation. Two matrices are multiplied. How the matrix multiplication can be done? First, we need to check whether the multiplication can be possible or not. If I am observing the first matrix, which is of order 2 by 3, that is having 3 columns, and the second matrix is of order 3 by 2, having 3 rows, we can say that their multiplication is possible and the resultant matrix is come out to be the order of 2 by 2. But how this C1 1 C12 C21 C22 comes out? For that, we move for the multiplication. There are two methods for doing the multiplication. The first is each element of first row multiplied to the each element of the column of the second matrix. First matrix row elements are multiplied to the second matrix column elements. So we are moving from uh, row to column. A11 is multiplied to B11 plus A12 is multiplied to B21 plus A13 is multiplied to B31, and we denote is equals to C11. Similarly, A11 with B12 plus A12 with B22 plus A13 into B32, and we denote as C12. Now come to the row second, A21 into B11 plus A22 into B21 plus A23 into B3 is denoted as C21. Similarly, second row into second column, A21 into B12 plus A22 into B22 plus A23 into B32 is equals to denoted by C22. So C11, C12, C21, and the arrangement is shown in the resultant matrix. The successive multiplication of row I of A with column J of B, row by column multiplication. For example, a matrix A having element 1, 2, 3, a matrix A having element 1, 2, 3 in the first row. In second row, the elements are 4, 2, 7, and the matrix B or the second matrix having the element in first row is 4, 8, in second row is 6, 2, in third row 5, 3. So they need to get multiply. For doing the multiplication, check the condition for multiplication. The first matrix is of order 2 by 3 and the second matrix is of order 3 by 2. So the column of first is equals to the uh, column of first is equals to the rows of second. So we can say the matrix multiplication is possible. Now proceed as the row column multiplication procedure. 1 into 4 plus 2 into 6 plus 3 into 5. Now 1 into 8 plus 2 into 2 plus 3 into 3. Similarly, second row, first column, 4 into 4 plus 2 into 6 plus 7 into 5. 4 into 8 plus 2 into 2 plus 7 into 3. So the resultant matrix come out to be 31, 21, 63, 57. Remember, this is also the same. If any identity matrix is multiplied to any matrix, it is always come out to be the same, the matrix. So IA is equals to A. Keep it in mind. Now, assuming that the matrix A and B are conformable, A, B, and C are conformable for the operation indicated, the following are true. AI is equals to IA AI is equals to IA equals to A. Second, A bracket BC equals to AB into C equals to ABC associative law. Third is first distributive law, that is A B plus C is equals to AB plus AC. Second distributive law, that is bracket A plus B into C is equals to AC into BC, AC plus BC. Generally or precautionally, we can say that AB is not generally equal to BA. Generally, if you think about this, that AB is equals to BA. No, it cannot be. AB is not equals to BA. Or BA may not be conformable also. Okay. So we cannot say that if A multiplied to B, then B can be multiplied to A. Second, if AB is equals to 0, this means neither A nor B necessary equal to 0. If AB equals to AC, so we cannot say that B not necessarily equal to C. Okay, B is not equal to C, not necessarily. These are the some fundamental properties of multiplication. Next, AB not generally equal to BA. BA not may not be conformable. For trying to see this result, let's suppose a matrix T of order 2 by 2, 1, 2, 5, 0, and the second matrix S of order 2 by 2 having element 3, 4, 0, 2. Now we perform T into S first, and after performing T into S, we perform S into T. So when you perform T into S, yes, T into S can be done as number of columns of first is number of rows of second. So the multiplication can be done and the resultant matrix is of the 2 by 2 also. So as per the row into column multiplication procedure, the result come out to be 3, 8, 15, 20. And in case of ST, if I multiply S with T, then the resultant come out to be 23, 6, can 0. So we can say that TS is not equals to ST in general, or we can say that AB is not generally equal to BA. Okay. If AB is equals to 0, neither A nor B necessarily equals to 0. For matrix A, the elements are 1, 1, 0, 0. For matrix B, the elements are 2, 3, minus 2, minus 3. When you just perform the matrix multiplication procedure, row column, then it come out to be 0, 0, 0. So the result come out to be 0. That means here is the proof. We had seen that the elements of A, or we can not say that directly that A or B necessarily is 0. They can be 0 or they cannot be 0. If they are not 0, then the result come out to be 0 is not making sure that the elements of all the elements of A and B are necessarily equals to 0. Now transpose of matrix. Transpose is just basically, in general, we can correlate this transpose word with the reciprocation or reciprocal. If any matrix of order 2 by 3, 2, 4, 7, 5, 3, 1, the transpose of A denoted by AT. First of all, any matrix, and if you want to take the transpose of that given matrix, and the representation is denoted by A dash or A transpose. And A transpose means you are changing rows into column and columns into row. So A transpose equals to, and the order will automatically change. For A matrix, the order is 2 by 3, and A transpose, the order is 3 by 2. In general, Aij is equals to A transpose Ji for all I and J. So this is the transpose of matrix, a very simple concept which is to be used for further calculation while calculating the inverse and all that. To transpose, we interchange the rows and columns. To transpose, we interchange the rows and columns. That is, we are converting rows into columns and columns into rows. The dimensions of A transpose are the reverse of the dimension of A. Obviously, when you are interchanging the rows into columns or columns into row, the dimension or the size will be the reverse of the original matrix. As you see in the example. Now, properties of transposed matrix.